illustrated by John Bradford Abelard Schumann. Third revised edition by Isaac Asimov. Diagrams by John Bradford. Inside the Atom, originally published in 1956, was so widely acclaimed by major reviewing media that it has been revised periodically to incorporate the newest findings in the complex and fascinating world of the atom. In this third revised edition, Dr. Asimov has developed new material that tells the story of the neutrino, which in recent years has been the most exciting part of the world inside the atom. New information on mesons, hyperons, and strange particles has been included, as well as details concerning the connection between atomic research and astronomy. Also described is additional material on the development of the atomic theory, the periodic table of elements, cathode rays, the discovery of radioactivity, the photo-electric effect, matter waves and cosmic rays. In his usual thoroughgoing manner, Dr. Asimov has also updated earlier material on atomic technology, in connection with atomic power plants, atomic submarines, the Test Ban Treaty and the Chinese A-bomb. AGS, Abelard Schumann. London, New York. SMUSD Berlin Game HS 539.7 ACI Asimov, Isaac, 1920. Inside the Atom /UVTI trim _ 33473 800082935. Berlin Game, California. WHLOO += SWVOOLs. EATATED APEULE4, by MIINFF Han Edway Hath La EEEELE at ES. Abelard Schumann. Books by Isaac Asimov. The Chemicals of Life, Races and People, with William C. Boyd, Building Blocks of the Universe, revised edition, Only a Trillion. The World of Carbon, the World of Nitrogen, The Clock We Live On, revised edition, The Living River, The Ringchium of the Sun, revised edition. The Wellsprings of Life, The Double Planet Inside the Atom, third revised edition, Environments Out There. Abelard Schumann. To Charles R. Dawson, ISBN 0-271,444-9. Copyright 1956, 1958, 1961, 1966 by Isaac Asimov. Library of Congress Catalog Card Number 66 to 11053. New York, London. Abelard Schumann. Abelard Schumann Limited 257 Park Avenue South, 158 Buckingham Palace Road Southwest 11001024 Market Square, Aylesbury. Published Indiana, Canada by Longman Canada Limited and in-text publisher. Printed in the United States of America. Designed by the Etheridge's OI0G1. Contents list of illustrations 7. Introduction 9. Atomic contents 13. What all things are made of. The two kinds of electricity, the unequal twins, the uncharged particle. Atomic arrangements 33. The massive center *, the frothy remainder, varieties of atoms *, sample elements, families of elements *, charged atoms. Atomic twins 53. A close look at an element. Isotopes, many and isotopes few, heavy hydrogen and heavy water. How isotopes were discovered, how isotopes are separated. Atomic breakdowns 69. Unstable atoms sent the three radiations, the different kinds of light. Gamma rays sent a new kind of energy. Atomic lifetimes 92. Radioactive slowdown *, the long-lived atoms, the short-lived atoms *, atomic arithmetic radioactivity at 83 and below. Atomic bullets 112. The alchemist's dream, getting past the electrons, a new kind of carbon sent, man takes a hand. Atomic artillery 128. New bullets. Copyright New Atom Smashers. New atoms sent new elements. Atomic newcomers 146. Opposites sent. Antimatter sent, the tiniest in between sent remaining puzzles. Atomic energy 161. Not exactly 1 *, the disappearing mass, the useful neutron *, neutron reactions, fission. The special case of uranium-235. Atomic dangers 178. The chain reaction that could work some of the difficulties. The atomic bomb sent, the hydrogen bomb, the three effects fallout, the worst danger of all. Atomic hope 195. The delicate balance birth of the atomic age. Isotopes A plenty * power A plenty more fuel sent, the future index 217. Illustrations attraction and repulsion 18. Cathode rays and channel rays, charge and discharge subatomic particles and magnets, 28 masses of subatomic particles, 29 subatomic particles passing through atoms, 35 some simple atoms, 44 degrees similar elements, 47 some simple isotopes, 61 the mass spectrograph, 66 radioactive radiations in the presence of a magnet equals 74. Alpha particles and beta particles, 7 electromagnetic radiations, 84 matter into energy, 89 half-life, 97. A radioactive series, 104 to 105 the electroscope, 118 how carbon-14 is formed, man-made transmutation, bombardment by protons, artificial radioactivity, mass energy diagram, I mass energy diagram, 2 the deuteron, 169 chain reaction, 173 mass energy diagram, 3 mass energy diagram, 4 atomic power, 189 121 125 131 140 163 164 176. On October 4, 1957, the Earth gained a small new moon called Sputnik, and Americans were suddenly shocked to find that in some ways they were falling behind the Soviet Union in scientific accomplishment. The immediate result was a great number of speeches by many men to the effect that America must revamp its educational system, especially in the physical sciences. And perhaps we will now indeed do this. Yet it all comes late. Sputnik did not create a crisis, it merely advertised one. For years, scientists have worried about the decline in science teaching at a time when science was becoming more and more important to our well-being. The high schools with good courses in mathematics, physics, and chemistry were becoming fewer in number. Fewer scientists, engineers, and technicians were being turned out by the colleges each year. The good science teachers were practically disappearing. But warnings about such matters fell upon deaf ears until Sputnik. Even Sputnik, however, can be misinterpreted. It would be quite wrong, for instance, to suppose that the only reason we must suddenly worry about science is that we must have better missiles quickly, or that we are in a scientific race with the Soviet Union. Not at all. Even if the Soviet Union did not exist and if all nations were friends, even then the need for scientists would be vital. The Earth now has a population of close to 3 billion and it is mounting daily. America's population, now approaching 200 million, has the highest standard of living of any people in history, and other nations, less fortunate, are trying to raise their own as high. But a record high standard of living for a record number of people is made possible by only one thing, the machine. 3 Machinery helps grow more food, helps dig into the ground for more ore to convert into more metal, builds and maintains our cities, carries us and our goods over land and sea and through the air, runs our homes, entertains us and keeps us comfortable, even does our mental work for us. If ever our machine civilization were to fail us, even for a short time, starvation and complete disaster would follow. Human muscles alone, without machinery, couldn't support our present society even for a day. But all our machines depend on energy obtained from the burning of oil or coal, and our oil and coal won't last very much longer. We will need new sources of energy soon to keep our machinery going: energy from uranium fission, energy from hydrogen fusion, energy directly from the sun. Our machinery is built out of metal, and when the supply of certain metals runs low, we must find new sources. We must learn to use low-grade ore or seawater as a source. Or else we must find substitutes, new ways of using glass, plastics, natural and artificial fibers. As population continues to increase, we must find new ways of producing and handling food, new ways of fighting insects, weeds, and other pests, new and more efficient ways of housing people and moving them from place to place. Naturally, we all want to be spared the ravages of disease and pain. We want to live longer and be healthier. We want to be protected from flood, fire, and disaster generally. There is, perhaps, even the great adventure of space travel lying ahead of us in the not-too-distant future. None of this involves the Cold War or the Soviet Union. All of this, on the other hand, involves science, more science and more scientists. But in order to get more scientists, we must start with young people. It takes time and training to become a skilled research scientist just as it does to become a skilled athlete. In both cases, an early start improves a youngster's chances. A book such as this one is my way of contributing toward a possible early start. However, that is not the only reason for the book. It's a mistake to think that there is no point in becoming interested in science if you don't intend to be a scientist someday, or that there is no longer any point to reading about science if you have finished your schooling. Consider baseball instead of science for a moment. Baseball is our national sport and there are few of us who don't know the difference between a base hit and a fielder's choice. Yet the percentage of professional baseball players in our population is extremely small. Would you think that there's no point in being interested in baseball if you are not going to make your living at it? Of course not. There is, after all, a pleasure in being a spectator, too. If baseball is properly understood, watching two fine teams play a tensely fought game adds to the enjoyment of life. It makes it possible for us to experience thrills and excitement. It gives us hopes and triumphs, yes, and sorrow, too, but a sorrow that is washed out in the thought of a better break tomorrow or even next year. But without an understanding of the game, we lose all that. If we were to watch a baseball game without knowing the rules or being aware of the fine points, we would see only a group of men chasing a ball. And so it is with science. Science has become part of our lives and we can't hide from it any longer. It is all about us, touches everything we do. Only a few of us can be research scientists, perhaps, but all the rest of us, whether we like it or not, are spectators. We can be spectators without understanding and the whole thing will only puzzle and worry us. Or we can learn some of the rules of the game, so to speak, perhaps not enough to make us scientists, but enough to make us appreciative spectators, science fans, in a way, who know when to be excited and when to cheer. There is active pleasure in knowing, in understanding. If we do no more with our learning than look at the world about us with more understanding eyes, it will have paid for itself many times over. And there is always the chance that someone will start to learn with only the intention of being an appreciative spectator and end by finding himself part of the game. Inside the atom is an attempt to explain some of the fine points of the atom and what goes on inside it, how man has learned about it and what he has done with his learning. What all things are made of. There are so many things in the world that are so completely different from one another that the variety is bewildering. We can't look about us anywhere without realizing that. For instance, here I sit at a desk, made out of wood. I am using a typewriter made out of steel and other metals. The typewriter ribbon is of silk and is coated with carbon. I am typing on a sheet of paper made of wood pulp and am wearing clothes made of cotton, wool, leather, and other materials. I myself am made up of skin, muscle, blood, bone, and other living tissues, each different from the others. Through a glass window I can see sidewalks made of crushed stone and roads made of a tarry substance called asphalt. It is raining, so there are puddles of water in sight. The wind is blowing, so I know there is an invisible something called air all about us. Yet all these substances, different as they seem, have one thing in common. All of them wood, metal, silk, glass, flesh, and blood, all of them are made up of small, separate particles. The earth itself, the moon, the sun, and all the stars are made up of small particles. To be sure, you can't see these particles. In fact, if you look at a piece of paper or at some wooden or metallic object, it doesn't seem to be made of particles at all. It seems to be one solid piece. But suppose you were to look at an empty beach from an airplane. The beach would seem like a solid, yellowish stretch of ground. It would seem to be all one piece. It is only when you get down on your hands and knees on that beach and look closely that you see it is really made up of small, separate grains of sand. Now the particles that make up everything about us are much smaller than grains of sand. They are so small, in fact, that even a microscope could not make them large enough to see, or anywhere near large enough. The particles are so small that there are more of them in a grain of sand than there are grains of sand on a large beach. There are more of them in a glass of water than there are glasses of water in all the oceans of the world. 100 million of them laid down side by side would make a line nay half an inch long. Underscore these tiny particles that all things are made of are called atoms. How many different kinds of atoms are there? When you think of the millions of different things in the world, you probably suppose there must be millions of different kinds of atoms. That is not so. The number of kinds of atoms known today is exactly 103. That's all. Just 103. What's more, many of these 103 varieties are very rare. Some occur only in certain uncommon rocks. A few of them are manufactured by scientists and don't exist at all except in laboratories. In fact, about 99% of everything on Earth is made up of only about a dozen different kinds of atoms. Such things as sugar, starch, wood, cotton, and vinegar are made up of only 3 kinds of atoms, the same 3 kinds in each case. The reason for the variety on Earth is that even a few kinds of atoms can be arranged in many different ways. It's as though you were considering threads of only 3 or 4 different colors. The number of colors may be small, but the threads can be woven into millions of different designs. By now you may be asking, if atoms are so small that we can't see them, how do we know that they really exist? Well, for hundreds of years now, scientists have been trying to determine why some substances burn when they are heated, why some fizz and some explode, why other substances rust in damp weather, and so on. They have experimented in order to find out why the materials that make up the Earth behave as they do under different conditions. This type of study is called chemistry. In order to explain the results of their experiments, chemists finally decided that the small particles called atoms exist. Unless there are atoms, there is no simple way of explaining many of the discoveries that chemists have made. This modern atomic theory, the ancient Greeks had one, too, was first proposed in 1803 by an English chemist named John Dalton. In the 150 years since then, all the experimental evidence has continued to back up this notion. Today it scarcely seems possible to doubt the existence of atoms even though we never see them. Are atoms the smallest things of all? At first it was thought so. The very word atom, in fact, comes from a Greek word meaning uncuttable or unsplittable. The idea was that with the atom we had gotten down to rock bottom. It couldn't be cut. It couldn't be split. There was nothing smaller. For nearly 100 years, chemists thought that. Then, in the 1890s, scientists studied some of the events that take place when an electric current passes through a vacuum, and they came to the conclusion that particles smaller than atoms do indeed exist. It turned out, in fact, that all atoms are made up of these still smaller particles. These new extra small objects are called subatomic particles. The 2 kinds of electricity. There is a long history leading up to that discovery in the 1890s. It turns out that people had observed the effects of subatomic particles, without knowing it, long before they suspected the existence of such particles. The ancient Greeks, for instance, some 2,500 years ago, noticed that if a piece of amber, a yellowish, glassy substance, is rubbed with fur or cloth, it suddenly becomes able to attract light. Objects such as small feathers or bits of wool. Beginning in 1570, an English doctor, William Gilbert, was studying this odd behavior of amber. He found other substances which acted in the same way. Since the Latin word for amber is electrum, Gilbert called all substances which could be made to show a force of attraction, on being rubbed, electrics. Soon people came to call that force of attraction electricity. Then, in 1733, a French experimenter, Charles François Dufay, found there were 2 kinds of attractive forces, 2 kinds of electricity. A glass rod and a rod of sealing wax, he found, if rubbed with silk, both become electrified. The glass rod attracts small objects, and so does the sealing wax. Suppose, though, that 2 electrified glass rods are hung by silk threads near each other. When this is done, the two rods swing away from each other. They repel each other. Exactly the same thing happens if two electrified sealing wax rods are hung near each other. They repel each other, too. Now suppose that a glass rod and a sealing wax rod are hung up near each other. These two rods swing closer together. They attract each other. So, you see, there seems to be one kind of electricity in glass and a second kind in sealing wax. Two objects containing the same kind of electricity, such as two glass rods or two sealing wax rods, repel each other. Two objects containing different kinds of electricity, such as a glass rod and a sealing wax rod, attract each other. Benjamin Franklin, the famous American patriot of Revolutionary days, studied electricity in the 1740s. As a result of his experiments, he suggested that there was one kind of electricity that moved from object to object. Some objects would pile up more than the normal amount of electricity. Others would have less than the normal amount. Franklin was the first to speak of a positive charge of electricity and a negative charge. In 1800, an Italian scientist, Alessandro Volta, devised a method of putting metals together in such a way as to construct an electric battery. This was a device which could produce a moving current of electricity. Attraction and repulsion. Two glass rods, both with positive electric charges, GOE-like charges, repel each other. Two sealing wax rods, both with negative electric charges, SRI-like charges, repel each other. Pi glass rod, positive electric charge, sealing wax rod, negative electric charge, 7 Higgs unlike charges attract each other. E19 * atomic contents. Every battery had a positive pole, which was also called an anode, and a negative pole, which was also called a cathode. People working with such batteries guessed that the electric current traveled from the positive pole to the negative pole. They had no way of telling whether they were right, it was just a guess. The guess turned out to be wrong. As long as the electric current passed through wires or through liquids, it was impossible to tell in which direction it was moving. What if the current were made to pass through a region where there was nothing at all, through a vacuum, in other words? Once scientists had learned how to prepare containers from which almost all the air had been pumped, they were ready to go. Such a vacuum tube could be made which contained an anode and a cathode, and electricity could be forced through. It turned out that a glowing stream of electricity originated at the negative electrode, the cathode, and shot straight across the tube in a straight line. In 1876, a German scientist, Eugen Goldstein, called the rays in this stream of electricity, cathode rays, because they started at the cathode. In 1886, he made use of a special cathode in which he had bored holes or channels. He found that, in using such a cathode, a different set of rays could be made to appear. These passed through the channels and moved in the opposite direction from that in which the cathode rays moved. Goldstein called these new _rays channel rays. For years, scientists wondered what these rays might be. Were they a new kind of light, or were they streams of tiny particles? Finally, in 1897, an English scientist, Joseph John Thomson, was able to show that the cathode rays consisted of one kind of very tiny particle, a particle much smaller than any atom. It was the first subatomic particle to be discovered. Because an electric current is made up of these particles in motion, they came to be called electrons. In 1906, Thomson received a Nobel Prize for this discovery. The channel rays also consisted of particles, but of particles of different kinds, none of which were electrons. Some of these channel ray particles were smaller than others. In 1914, a New Zealand-born British scientist, Ernest Rutherford, suggested that the smallest of the channel ray particles be called protons. This suggestion was adopted. As it turned out, both electrons and protons carried an electric charge. The electron carried a negative charge, and the proton carried a positive charge. They were the particles making up the two kinds of electricity discovered by Dufay. However, the electron moved from object to object much more easily than the proton did. When electrons moved from object A to object B was filled with a greater than normal quantity of electrons and carried a negative charge. The more electrons crowded into object B, the greater its negative charge. In the same way, object A, having lost electrons, was left in the opposite condition and carried a positive charge. The more electrons left object A, the greater its positive charge.